Hi everyone, my name is Peter. I'm an ML enthusiast. Today I'll tell you how modern neural networks use multiple GPUs. Then I'll show you in code how this all works. I have been working on this video for way too long, so the codebase here is quite outdated. Nevertheless, the information is still correct, so I recommend watching. Before we begin, I want to discuss why I decided to make this video. I was inspired by a fascinating project by Andrey Karpathy, who is a prominent researcher formerly working at OpenAI and Tesla. So he developed a project called llm.c, which is a GPT-2 neural network implemented entirely in C language and some CUDA code. The purpose of this project was to serve as an educational material, mostly helping people to understand how neural networks function at a very fundamental level, without using any of the machine learning frameworks like PyTorch, TensorFlow, and JAX. I decided to extend this project by implementing training on multiple GPUs in my free time. And to be honest, this seems like a good opportunity to explain the inner workings of these networks and how they work. In this video, I will explain why neural networks require multiple GPUs. Then I'll discuss the algorithm for training on multiple GPUs. Then I'll present what llm.c is. Then we will enhance llm.c with multiple GPU support, and I'm going to walk you through the entire process. If you're familiar with some parts of this presentation, feel free to skip ahead. Timecodes are in the description of the video. Let's begin by asking ourselves, why do neural networks need multiple GPUs in the first place? Companies like OpenAI, Meta, Google have surely considered efficiency. They use thousands of GPUs to train these models. Could they manage with just one GPU? What is the compelling reason for using more? To answer this question, I wanted to explore the history of GPU in neural networks and see how it all got started. Let's get back to 2012. During a significant competition hosted on the ImageNet database. ImageNet is a database of images across various classes, and the challenge was to develop an algorithm to accurately classify these images. The competition featured 1.2 million images spread across 1,000 categories. You can see some examples in the video right now. There are different dog breeds, houses, people, fish, etc. So back in 2012, they had a competition with 7 teams on it. And the question was, who can classify these images the best? Who can implement the algorithm that can classify these images the best? If you look at the results, we'll see that the winning team, Supervision, achieved an error rate of 15%. And this is significantly better than the second best team, which had an error rate of 26%, which is a full 10% higher. So how did they manage that? Turns out that the team, led by Alex Kryzewski, Ilya Sutskever, and Geoffrey Hinton, revealed that their model was a large, deep convolutional neural network. The network had 60 million parameters, and importantly, it was trained on 2 NVIDIA GPUs for about a week. This was our first successful implementation of a neural network that is actually capable of solving practical tasks better than classical algorithms. And it was using multiple GPUs right from the start. Why is that? If you read the paper, we see that they explain the reason behind it. According to it, a single GTX 580 has 3 GB of memory, which limits the maximum size of the networks that could be trained on it. We see that they had only 3 GB of RAM, and it wasn't enough. Moreover, they further say, in the end, the network size is limited mainly by the amount of memory available in current GPUs, and by the amount of time that we are willing to tolerate. So they even predict their experiments can be improved by simply waiting for faster GPUs and bigger datasets. By the way, this was actually true. They concluded that the usage of 2 GPUs was mainly for 2 reasons. First, the network wouldn't fit on a single one due to its size. Also, the amount of training time that they were willing to tolerate is limited. And this actually stays the same. These are exactly the 2 reasons why we use multiple GPUs. We often have this problem that a network wouldn't fit on a single one, and the second part is that the amount of training time we can tolerate is limited. But one can ask, why can't we just wait for bigger and faster GPUs with more RAM and more compute? Well, the problem is this. In the past 10 years, the sizes of neural networks have increased significantly. A graph on the slide shows that since 2020, the parameter count of published neural networks has doubled approximately every 6 months. And this greatly exceeds any hardware advancements that we can make. You cannot simply double the memory size and compute every 6 months. This is too unreasonable. So, to recap, multi-GPU training has been essential from just day one of using neural networks on GPUs. And we use multiple GPUs both to fit the models and to reduce training times. In this video, we will focus specifically on the second issue. Let's assume our model fits perfectly on a single GPU, but we just want to wait for too long to complete the entire task. So here is the question: how do you train on multiple GPUs? Let's examine another paper, not from 12 years ago, but just from 10 years ago. The paper describes an algorithm behind the VGG network. Here is what the authors say. Multi-GPU training exploits data parallelism and is carried out by splitting each batch of training images into several GPU batches processed in parallel on each GPU. And the GPU batch gradients are computed. They're averaged to obtain the gradient of the full batch. Gradient computation is synchronous across the GPUs. So the result is exactly the same as when training on a single GPU. Let me break this down. This is going to involve a little bit of math, but if you already know the algorithms or it's too overwhelming, feel free to skip this part. To fully understand this, let's revisit how neural networks function. I use a simple GPT network as an example. The network takes an input sequence, predicts the next word, and learns from corrections during training. For instance, consider the input phrase, a quick brown fox. The phrase is fed through several layers of the network, and the network's output is an attempt at the next word. In our example, the network might incorrectly predict the next word delf, which is not what we want. This is where the training data becomes crucial. It indicates that the correct word following a quick brown fox should be jumps, and we use the loss function to measure how far off the network prediction are from the correct word. The loss function compares the predicted output delf to the actual desired output jumps, determining the error or the loss. Let's dig deeper into the training process itself. Let's take a look at an example where we have 4 sentences as input to the neural network. Each of the inputs gives us a prediction. In total, it's 4 predictions. For each prediction, we have a correct response from the training dataset. We calculate the loss for each of the pairs, L1, L2, L3, and L4. These are the losses on each of the examples. And the overall loss is going to be determined by the average, L1 plus L2 plus L3 plus L4, and all of this divided by 4. This process that I described is actually known as the forward pass of the neural network, and this happens during training. We assess the network performance based on the computed loss value. After the forward pass, we do a backward pass, and this is basically going through the same network but backwards from output to input. We analyze the loss and calculate the gradient with respect to weights across all of the layers. And the gradient is going to inform us how we need to adjust the weights to improve the loss so that it can lead to better results. The final step is going to involve applying these calculated gradients to update the weights. We take a small step called delta, multiplied by the gradient, and adjust the weights slightly towards the optimal values. This adjustment will reduce the loss and lead to better predictions. This is the gradient update step. Now, let's get to this thing from the VGG paper, exploiting data parallelism. What does this exactly mean? Imagine we have the same 4 examples as before, but this time we have 2 GPUs instead of 1, and we want to use both of them. Here is how we can do it. We'll assign the first 2 sentences to the first GPU and the next 2 sentences to the second GPU. So let's proceed with this setup. Everything stays as is. We just use the same algorithm and feed and just run 2 copies of it on different GPUs. On the first GPU, which is handling the first 2 examples, the computed loss is going to be L1 plus L2 divided by 2. We will call this LGPU1. Similarly, on the second GPU, which processes the third and the fourth example, the loss is going to be L3 plus L4 divided by 2. We are going to call this LGPU2. Let's continue and examine what's going to happen during the backward pass. We have already calculated the loss on each GPU, and during the backward pass, we update the gradients for each of the GPUs. For the first GPU, the loss is going to be calculated with respect to the weights as delta LGPU1 divided by delta W. Similarly, for the second GPU, the gradients are computed as delta LGPU2 divided by delta W. Next, let's just proceed with the same thing and see what's going to happen if we initiate the gradient update step independently on 2 of the GPUs. Well, it becomes evident that the first GPU updates its weights based on the gradient computed on the first batch of LGPU1. Meanwhile, the second GPU updates its weights based on its own gradient, LGPU2. And these two updates actually result in different weights on each GPU. We are essentially just training two copies of the same neural network, but on two different datasets. And this is not going to be an optimal use of our GPUs. How can we fix that? Let's take a look at what is the core issue here. As I mentioned earlier, the gradients on different GPUs don't match the true gradient that would be computed for the entire 4 examples. Ideally, we should compute the gradients as if we had the four examples together, but distributed across the 2 GPUs. This is where we are going to apply a little bit of math. If this sounds too complex, feel free to just skip ahead as I mentioned before. So, the first GPU computes the average loss for the first 2 values as L1 plus L2 divided by 2. And the second GPU computes the average loss for the last 2 examples as L3 plus L4 divided by 2. The real loss we aim to work with is the average of the 4 examples, not just 2 on 2 different GPUs. And this is going to be calculated as L1 plus L2 plus L3 plus L4, and all of this divided by 4. Now, let's incorporate this into the total loss formula of the gradient calculation with respect to the weights. You see that if we kind of arrange this formula a little bit, we can see that this is possible because of the linearity of the gradient. It turns out that the average of all individual GPU gradients accurately represents the gradient of the total loss on all 4 examples. So let's write this formula once again. We see that we just need to compute the gradients of each of the GPUs independently, and then we just average them out. And this is going to give us the total gradient as if we had 4 examples on the single GPU. Now let's visualize the timeline of a single training step when we use multiple GPUs. Each GPU is going to load some examples. It's going to perform a forward pass and then a backward pass. All of this is pretty exactly the same as having a single GPU. The only key difference is going to be is that in case of multi-GPU training, we need to average the gradients across all of the GPUs. And this is actually what makes it different from training on a single GPU. For actually averaging the gradients across different GPUs, we use a special algorithm that is called allReduce. If you are curious to know how allReduce works and know the mechanics behind it, how it handles all of the computation, communication between different GPUs, all of that, feel free to leave a comment down below, and I'm going to make a video explaining about it in detail. After all of this is cleared, let's talk about llm.c. Once again, llm.c is a program that is developed by Andrey Karpathy, a renowned researcher formerly working at OpenAI and Tesla, and this is a minimal implementation of a GPT-2 model, essentially just a precursor of ChatGPT or a grandfather to ChatGPT if you want. And this is contained in less than just 3,000 lines of C code. This strips out all of the complexity of Python, PyTorch, JAX, TensorFlow, all of these frameworks. And actually, interestingly, it runs 20% faster than PyTorch at the moment. Moreover, we are even exploring the ways to optimize it even further. And this single file setup makes llm.c is an ideal learning resource. It is quite small and gives us a fantastic opportunity to implement multi-GPU training for the real GPT-2 model and explore the deep underlying mechanics of libraries we use, such as PyTorch. So, with all of this information, let's now focus on adding support for multi-GPU training to llm.c. Welcome to the llm.c repository. Here you'll find the manual that guides you on running this program to train a GPT-2 model. If you're interested in a detailed guide on setting up llm.c, I recommend a tutorial video by Dryden, link in the description. The link to the llm.c repository is also in the description below. Let's move on to VS Code. The main change to the original GitHub I've made is the removal of multi-GPU support from the code. This is intentional. This will allow us to reintroduce multi-GPU support through the video. Let's start by compiling the code. The command you see now compiles the binary, after which you can run it. The script begins the training process, and you will notice that the loss value is decreasing steadily over time. Periodically, the script will generate some text, improving equality as the training progresses. However, at the moment, it is configured to use just one GPU. We will proceed to reintroduce multi-GPU support right now. To accomplish this, we need to include a library called mpi.h. This library will enable us to run multiple copies of the same process on different GPUs. But before we start writing any code in C, let me explain how MPI works in general. To run a program with MPI, we use a command called mpi run. You specify the number of processes you want to run, and then you specify the program you want to execute. In my example, I will simply print hello world with a built-in echo command in Linux. Also, I will include some MPI environment variables, which will be clear in a moment. MPI will execute 10 copies of this command simultaneously. MPI assigns an index to every process that it runs. As you can see in this example, each hello world receives a different number. This is extremely useful for us. We can assign a process number 0 to GPU 1 and process number 1 to GPU 2. These two processes will run concurrently, and with the help of MPI, they are able to communicate with each other and perform the training. Now, let's integrate MPI into our application. We'll start by going into the main function. Initially, we'll just return from the function immediately. This will allow us to experiment a little bit before diving into the full training process. Then, I'm going to create an empty function named multi-GPU-init and call it from our main function. The first thing required for MPI is to initialize it with mpi init at the beginning and to finalize it with mpi finalize at the end. These calls are necessary for MPI to function correctly. Once we initialize MPI, it is important to understand two key concepts: rank and world size. Rank is the unique identifier for each process, and world size indicates the total number of active processes within the environment. In our function, we will use mpi.rank to determine each process's rank, and mpi.size to find out the world size. This information is crucial as it allows each process to know its role and how many peers it needs to communicate with. The MPI API requires us to pass a communication channel. We will use the default one. We will add a simple print statement that outputs hello world along with the rank of the process and the total world size. This will give us a clear example of how each process identifies itself and understands the scope of the environment. If we compile and run it, we once again see that each copy of the program prints its own string. Printing the rank and world size showcases basic MPI functionality. However, it is real power in making computations across multiple processes and aggregating the results. We have mentioned the all reduce algorithm previously in the slides. Now, let's demonstrate all reduce in action. Each process will generate a number based on its rank, and MPI all reduce will sum these numbers, sharing the result with all processes. As you can see, process 0 has generated its value 1, process 1 has generated its value 2. And after all reduce, they all got number 3, which is indeed the sum. So you can probably already see how this can be useful. In our example, the value we are aggregating in all reduce is just the rank plus 1, but we can compute more complicated values. For example, the gradients of a neural network. They are really expensive to compute. You may ask, what if one GPU runs faster than another? What does happen if our processes reach all reduce at different points in time? Let's simulate an expensive computation by adding a sleep into our program. Process 1 is going to sleep for 1 second. It is going to simulate a heavy task. As you can see, everything still functions normally. In fact, when different processes take different amounts of time to execute, MPI will force some of them to wait, so we don't really have to think about this as much. Another MPI primitive we have to know is called broadcast. It is useful when one of the processes has some value that it wants to share with others. Let's make process 0 set the value to 42, and process 1 will use the default of -1, and then call MPI broadcast to distribute this value to other processes. You can see that process 0 before the broadcast prints 42, while process 1 prints -1. But after the call to broadcast, the value got distributed to all processes, and they all print 42. Now that we have seen how MPI can perform distributed computations, let's refactor our code. Instead of just executing commands within our small function, we'll modify it to return a struct containing information about the process rank and world size. This structure will allow other parts of our program to access this configuration data easily. Alongside the initialization function, we'll create a cleanup function. We'll move out mpi finalize there. Let's use these two functions in our main program now. With that, we are ready to start using multiple GPUs. Let's scroll a bit through the main function. And you'll see that there is a call to the function named CUDA-setDevice. What it does is just selects the GPU from the one that we have on our machine. Currently, it is set to use only the first GPU. Instead of setting this value to just 0, let's replace it with the rank of the running process. Additionally, the call calls CUDA getDevice properties. The program just needs to get some properties about the GPU it's running on. Let's set the appropriate GPU index there as well. If we compile and run the program now, we can see that we are using 2 GPUs instead of 1. We see this because print statements are duplicated. However, what we are doing is just running 2 training runs at the same time with exactly the same parameters. If you scroll up a bit, we see that when the training starts, the first printed loss values are exactly the same. This is because they train on exactly the same data in exactly the same order. Let's verify that. There is a function named dataLoader next batch. It is called in the training loop. It loads a chunk of training data from a file. Let's print out the first 20 tokens. A token is an integer, which represents a part of a word. If you want to know more about tokens in GPT-2, I recommend a video from Andrey Karpathy about it. Link is in the description. To do that, we call it tokenizer_decode function. Since it is running multiple processes at the same time, we need to avoid calling printf in a loop. Instead, we concatenate our sentence into one string. It is a struggle to write this part. Operating strings in C is quite messy. We use a string buffer of a fixed length to avoid calling malloc. Then, we use sprintf to add a detokenized word to our string. We advance our string length variable by the number of added characters. Honestly, this is one of the reasons why I find C++ to be a lot better. Let's break out of the training loop right after we printed everything, just so we can see the printed results. As expected, we see that both of the processes got exactly the same data chunk. However, we actually want different processes to load different data. Let's take a look at how these data loaders are initialized and what they do. We see that the dataLoader next batch function works roughly like this. The function takes a dataLoader struct. It contains the current state of the loader. First, it writes the batch size and sequence length to local variables. Batch size is the number of sequences we need to feed to our GPT model, and the sequence length represents how long each sequence is. Then the function checks if you're at the end of the file, and if so, loops the file back to the beginning. Third, it moves to the current position in the file by calling fseek. After that, it reads b times t plus 1 tokens from the file. At the end, it advances to the current position in the file. To understand how to modify it for multi-GPU support, let's first visualize how the file is read. Here, the training data is represented as a continuous line. Each block represents a single batch of data. If we have one GPU, we have only one process. It starts reading the data from the beginning of the file. It does it in chunks of size b times t. It reads the first chunk, then the second one, and goes on until the very end of the file. Let's say we have more than one GPU. In our case, 2 GPUs. We have 2 processes. Each process reads a chunk of data with the size of b times t. Together, they have read b times t times world size tokens. So every process needs to start reading from its rank times b times t. Then, on every step for every process, we shift the starting position by b times t times world size. Now, let's modify the code to implement this idea. First, we go to the dataLoader initialization function. It should now take our multi-GPU config to get the world size and rank info. Let's move the definition of multi-GPU config struct to get rid of the errors. We would like to avoid passing multi-GPU config to every function, so let's copy the rank and world size into the dataLoader struct. Then we need to modify the init function. There is a check for the file size. It ensures that we have enough data to train on. We multiply the b times t by also the world size here. Then there is the current position initialization. We change it to the correct position depending on the rank of the process. Then there is this function that sets the total number of batches. We use it to determine how long we should train. We need to divide it by the world size here as well. there is the reset function. It resets the loader back to the beginning of the file. Instead of setting position to 0, we need to set it depending on the process rank. Let's go to the next patch function. It loads the new chunk of data and then advances the current position in the file. Then we once again need to change the way we reset the current position. Let's copy it from one of the previous statements. Then finally, there is the offset of the current position after we read a chunk. We again multiply by the roll size here. Interestingly, we can see that if we have only one GPU, nothing has really changed. When we reset the position, it is always going to be 0, because the rank is going to be 0. And when we advance the current position, the roll size is just 1, so nothing really changes. At last, let's change the way we call the initialization function and pass our multi-GPU config there. So let's compile the program and run it now. We see that now different processes read different data. That is actually good. Let's remove the debug prints and continue with training. Okay, compile and run again. We see that the loss values are indeed different now, even on the first step. But we still train two independent models, just on different data now. We need to aggregate the model gradients to train a single and unified model. Let's begin with aggregating the training losses. This is the easiest thing to do for now. It will be useful for us anyway. We will be able to see if our model is improving with this. You see that the training loop calls a forward pass in GPT-2 forward. It zeroes out the gradients in GPT-2 zero grad, and then does a backward pass in GPT-2 backward, and then makes a gradient update in GPT-2 update. As you can see, all of these functions take a pointer to the GPT-2 structure model variable. This variable contains all the necessary state to train the model. Specifically, we will be interested in the average loss and the gradients. If you remember from the slides, multi-GPU communication happens after the backward pass, but before the gradient update step. We are going to create an accumulation function. We are going to call this function there. First, let's go to the GPT-2 structure and add a new field, where we are going to store the average loss value between different processes. We'll call it accumulated mean loss. This variable is going to contain the average loss across multiple GPUs. Let's go back to the accumulation function. Let's call allReduce here to accumulate the loss. Now, let's print the accumulated loss in the training loop. Let's compile and run the program. We see that the program now correctly prints the accumulated loss. That's good, but we still train two independent models. We need to somehow also average the gradients on the GPUs. So far, we only handled losses, and losses are stored in the CPU RAM, because GPT-2 forward function copies the losses to CPU for us. But gradients are currently stored only in the GPU RAM. We don't want to move them to CPU RAM. It's going to be slow. Instead, we're going to average them right in the GPU memory. MPI could technically do that, but there is a better library. This library is called Nickel. It's created by NVIDIA exactly for this purpose. If you want to learn more about the differences between MPI and Nickel, leave a comment. I can make a video about that. We'll start by including the nickel.h library. Then we need to modify our multi-GPU config struct. We have to add a Nickel communication channel there. Let's call it nickel_com. With MPI, we could use the default communication channel mpi.com world. With Nickel, we cannot really do that. Nickel API requires us to call CUDA_set_device before using it. Let's move CUDA_set_device from the main function to multi-GPU init function. Then nickel requires us to create an ID in the first process and distribute it among other processes. This will be necessary to set up communication among the GPUs. We'll do that by creating a nickel unique ID variable. To do that, we call nickel get unique ID in the process with rank 0. We distribute this value to other processes using MPI broadcast. Finally, we call nickel com init rank to initialize nickel. We will pass all the necessary parameters. As always, we need to clean up the nickel communication channel when the program finishes. Okay, with nickel initialized, we can aggregate the gradients. Let's go to the GPT-2 multi-GPU accumulate function. We need to aggregate our gradients here. It's basically a single nickel all reduce call. The first two arguments are the send and receive buffer. We set them both to the gradient's memory pointer. Next, we tell it how many model parameters there are. It's going to tell it the size of our gradient vector. We specify the data type. We used reduced precision floats, where a number takes 16 bits rather than regular 32 bits. More specifically, we will use bfloat16 or brainfloat16. It is a 16-bit format designed specifically for neural networks. We provide the all reduce operation. In our case, it's the average. We specify nickel avg as the argument. Nickel needs a communication channel to communicate. Finally, we need a CUDA stream handle. We'll use 0. It tells CUDA that we are not overlapping any computations here. Just call the all reduce after the backward pass on the GPU is finally done. Okay, let's compile and run the program again. We see now that when the program generates some text, every token gets repeated twice. This is a good sign. This means that each of the processes has its own identical copy of the model. They are jointly training the same model now. This is all thanks to all reduce. We could average the gradients and share it with all GPUs. Every gradient update step in every process is exactly the same. Previously, we have discussed the math behind it. Because of it, our program now trains a single neural network. This is as if we were training on a single GPU, but with all the data for every step. Congrats! Everything is working now. Please leave a like. Now for a bonus part. Let's experiment a little bit and observe the speedups. There is a command line parameter that allows us to specify the batch size. Essentially, how many sentences a GPU sees during training. Let's set it to 8 and run on a single GPU. We see that a single step takes 430 milliseconds on average. Now let's run the program but on 2 GPUs. Since we use 2 GPUs, we divide the batch size by 2 as well, so we set it to 4. We see that a single training step takes only 280 milliseconds. This is 1.5 times faster than using a single GPU. It is not twice as fast due to some overhead, since GPUs need to communicate with each other, and this can take a significant amount of time. Also, let's try a batch size of 16 on a single GPU. We see a CUDA out of memory error. Let's try on 2 GPUs now. Each GPU will only need a batch size of 8. And as you can see, it works. Perfect. We are now able to process a lot more data than a single GPU would fit. Thank you so much for watching today's video, where we have dived into the essentials of multi-GPU training. We have covered the theoretical foundations, explored how MPI runs multiple processes, and discussed the role of NVIDIA's Nickel library in averaging gradients across multiple GPUs. There are some things I haven't covered in this video, but those would be necessary to create a full pull request. Implementing robust error handling, making MPI and Nickel optional, eliminating redundant print statements, and supporting various training precisions. I really appreciate you sticking with me through this entire presentation. If you enjoyed this video or have any questions, Please leave a like and comment below. It truly helps and encourages me to produce more content like this. Don't forget to subscribe for more in-depth discussions and tutorials. Goodbye and happy coding!